Hello everyone and welcome to MV Tutors. I'm Tselo and I'll be looking at the Maxwell-Boltzmann distribution diagram. Okay, it's just the last section on the rates of reaction. Alright, before I go any further, please don't forget to like our videos and also subscribe to our channel. And please guys, do spread the word, especially to those who will be in matric next year, 2022, and those who will also be upgrading their physics or maths marks. Okay, and again, if you want to book a session with us, go to our website www.mvtutors.co.za. Okay, so let us get to it. What is the Maxwell-Boltzmann distribution diagram? Well, basically, so you know that your particles, before they react, they do have energy, right? Kinetic energy, to be more specific. So here, the Maxwell-Boltzmann distribution diagram, it shows like a range basically of kinetic energy that the particles have, and we're going to now discuss shortly what is what and what energy is required to actually form reactions. Okay, so on the y-axis, okay, that is where we have the number of particles. Alright, and the x-axis, that's actually where we have the kinetic energy, mostly measured in joules. Okay, please don't mind me and I block those again. Yeah, I don't know, this December is not Decembering, so it's cold. It's quite cold, yet it's hot. Anyway, so yes, the y-axis is the number of particles, the x-axis is your kinetic energy. Okay, so I have under the diagram or under the distribution, I would call it distribution curve. Okay, in maths, if you were to describe the skewedness of this graph, would actually say it's skewed to the right. Okay, but yeah, in here we're mainly looking at the energy of the particles. So under the diagram where you have the yellow shaded area, okay, that's basically where you have the number of particles with energy that is smaller than your activation energy. Okay, so in this case, your particles are not able to react. Okay, remember when you look at your energy versus time graph, whether you have an exothermic or endothermic reaction, okay, there's a point where you talk about the activation energy. So if you see EA here, it's basically just the activation energy. All right, so yeah, under the yellow or rather the yellow shaded part of the diagram, it's your particles, but those particles, they do not have enough energy for reactions to form. All right, and then we have this green dotted line that basically is at your maximum point on your diagram. Okay, so I put it in green and I wrote there it's the most probable energy. So what does it mean when I say the most probable energy? Well, if you remember still maths, stats, for those of you who don't know where this maths is applicable, where science helps us to show us where it's applicable. So if you remember that you have a mode, you have a mean, and you have a median. Okay, so here this most probable energy refers to the mode. Okay, so basically it's your particles. In this case, your particles are likely to have this energy here. So if I actually had values, let's say this is 0 joules, this is 100 joules, and then we have 500 here. Obviously it's not to scale. Okay, so yeah, so let's say your most probable energy, basically a lot of the particles that you have, they average around 100. Okay, so that is basically what it means when it says the most probable energy. Basically your particles, the most probable energy they have, that's what it is there. So I hope I'm making sense. And then we get to the part that is shaded in purple. Okay, so this purple line here, okay, the vertical one. Okay, now I'm messing it up a bit. But basically that indicates the activation energy. Hence I put it as EA. Okay, and this activation energy, basically the particles under the part that's shaded in purple. Okay, you can't see my cursor, but yeah, basically the part here that is shaded in purple, that gives you the number of particles with energy that is higher than the activation energy. Okay, and if remember the minimum energy that is required for reactants to start reacting and forming products, that is the activation energy. So they have exceeded, those particles have exceeded the activation energy, and they are busy reacting and having effective collisions. Okay, so yeah, that is basically what's happening at the Boltzmann uh, diagram, Maxwell Boltzmann diagram. Now my question to you is, before I go and blow my nose, does this graph, okay, this distribution curve, ever touch the x-axis? Here we see at the beginning, it definitely starts at 0. Okay, because obviously if you don't have any particles, there is no energy. Okay, so that's why it starts at the origin here, at the x-axis. Sorry, at, yes, where the x and y-axis intersect. So it starts at 0. But my question is, here, does it ever get to a point where, it eventually touches the x-axis, or is it going to continue in an asymptote way, where it wants to touch the x-axis but never really touches it? Okay, so yeah, we're gonna take a young break and we'll be back. And we're back. Okay, so I left you with the question, does the graph ever touch the x-axis? Does this distribution curve or distribution diagram ever touch the x-axis? I spoke that it does start at 0, okay, because when you have 0 particles, there is 0 energy. Okay, there are no particles, there's no energy. But is this graph now going to eventually touch the x-axis, or will the x-axis actually act as an asymptote? Okay, so if you think about it, it will want to touch the x-axis. Okay, it will want to touch the x-axis, but your number of particles that get to that energy are actually quite little. So it will, let's see, let me try to sketch it again. Okay, so it will tend to touch the x-axis. Okay, yeah, it will tend to touch it, but it never will. So the x-axis will act as an asymptote. And why is that? Thing is, you can't really put a limit to the amount of energy the particles can have. They can get very big energies, but not a lot of particles can get there. And that is why as you head towards the x-axis, the fewer the particles there are that can actually reach those very high levels. Okay, so that's just out of interest. I was sketching it and I was thinking to myself, okay, the way I sketched it, it's as if there's an asymptote, but is there really? So when I did a little bit of research and reading, I did figure out, or rather I did learn, that it never touches the x-axis, nor will it ever cross it. Because if it crosses it, now you're saying you have a negative number of particles, and that just doesn't happen. Okay, so that is it with the graph. Now let us see, because in exams they like asking, like, what is the effect of increasing the temperature or cooling this reaction, or if we increase the concentration or reduce it, or if there's a catalyst, how will this graph look like? So we're going to start with the effect of temperature. Okay, if we increase temperature, so for this case I'm going to look at the increase of temperature, and here I'm going to look at the decrease of temperature. How will this graph look? What happens to the most probable energy? What happens to the activation energy? Does it shift? Okay, so let us get to it. So when you increase the temperature, what do you expect? We know that if you increase the temperature, the rate of the reaction increases, right? So when we look at this graph, when you are going to increase temperature, here's what's going to happen. With regard to the number of particles, okay, they won't change. Okay, so if you had 100,000 particles before you increase temperature, you're going to have 100,000 particles after you increase the temperature. So the number of particles, they don't change. Okay, but here's what happens. Your peak there, okay, it will have to reduce. So this is how the graph will now look. So it will look something like that. It will be much more flatter, okay, when you increase the temperature. So your most, what is it? Okay. The most probable energy will then shift to the right. Yes, I almost said left. It will shift to the right, okay? And then your activation energy, it's still, if maybe this value here for activation energy was like 300 joules, it'll still be 300 joules, okay? So this will now become your activation energy. Okay, so now the particles under the activation energy, like we said before, those are the ones that actually can react, form effective collisions. So yes, first of all, your most probable energy, it shifts to the left, right, shifts to the right. Okay, the number of particles, they don't change, they stay the same. Okay, but the number of particles that now have exceeded the activation energy are a lot, as opposed to the ones that are not involved in any reaction. Okay, so activation energy is still the same, but more particles have energy higher than the activation energy and can therefore react. Okay, so what can we conclude about it? Well, when you increase temperature, there are more effective collisions. So more effective collisions. Does collision have one L or double S? Okay, I'll check my spelling. So yes, so more effective collisions. So that pretty much is what happens when you increase temperature. But what happens now when you decrease temperature? So when you decrease the temperature, okay, the opposite will occur. Remember, when we increase temperature, this maximum number of particles that you had, they actually decreased for the most probable energy. Okay, but now when you decrease your temperature, your graph still starting at 0. Ooh. Let me start again. Okay, I think that's better. So now when you decrease the temperature, so now your most probable energy shifts to the left. Okay, all right, and then also still your activation energy, again, let's use the example of 300 joules, it's still there. Okay, but there are less particles actually that have energy that is higher than the activation energy. They have reduced, whereas the particles under well, this section here, where I'm just putting dots, you have a whole lot of particles under this area, and those particles will not react. Okay, so what happens to the number of particles? Like I said, temperature does not change the amount of particles that you have, so they don't change. Or we could also say that the number of particles remain the same. So what I forgot to say, if the number of particles remain the same, it means the area under the graph will always be the same. Okay, so if the area was like 5 meters squared, for the original graph, the blue graph, it will be 5 meters squared if you increase temperature or you decrease the temperature. Okay, so the number of particles, they remain the same. What happens to the most probable energy? Well, it shifts to the left if you decrease temperature. Okay, and then remember also, if this most probable energy shifts to the left, it just shows you as well that the number of particles that do not react have actually increased. If it has shifted to the right, it means that the number of particles that do not react or don't have energy higher than the activation energy, they have actually increased. No, they have decreased. Those particles that do not react, they have decreased, but the particles that do react have increased. Okay, so the activation energy, well, it is the same, 300 joules, right? But less particles have energy that is higher than the activation energy and therefore react. Okay, so yes, the activation energy is the same. We have 300 joules, but the particles that actually go to the other side of the activation energy that actually react, they are less. Okay, as compared to when you have your temperature increased. So what can you conclude therefore? Well, because there are less particles that actually react, you don't have as much effective collision. There are less particles that you have. Okay, those particles do not have kinetic energy that is higher than the activation energy, so therefore less effective collision, and therefore less effective collision. No, that does not look right. It definitely has a double L. So less effective collision, therefore your rate of reaction actually decreases. Here, I forgot to put that part. Here, your rate of reaction actually increases if you increase temperature, which is what we expect. Okay, so now we get to the part of the effect of concentration. What happens when you increase concentration and what happens when you decrease it? Okay, so if you increase concentration versus when you decrease concentration, what will actually happen? So when you increase the concentration, okay, of particles, guys, when you're increasing concentration, you're actually adding more particles are added, so the area under the graph will not remain the same as we had in temperature, increasing or decreasing temperature. The number of particles actually do increase when you increase concentration, and they decrease when you decrease concentration. Okay, so that's the first thing with the number of particles. Okay, the number of particles will increase. Remember the volume of the formula for concentration is number of moles over volume. Okay, so if you had a higher volume, you would have a lower concentration. Okay, but if you have a lot of number of moles, you have a higher concentration, so it makes sense that the number of particles will actually increase. Okay, so your graph will actually increase for your, let's draw it out. So this is what happens to your graph. Okay, it does something like that. So your most probable energy, it actually stays the same. That doesn't really change whether you increase the concentration or decrease concentration. So most probable energy, it remains the same. Okay, but obviously the number of particles that have the most probable energy, they have increased, right? So just as your number of particles have increased, also before you added or before you increased concentration, maybe they were like 1,000, particles. But now, with the increase of concentration, that 1,000 has increased to 2,000, for example. So it does, just because the most probable energy has stayed the same, okay, the energy that most particles are likely to have, it's the same, okay, but your number of particles have actually increased there. Okay, now, okay, I think I've actually sketched the graph not so correctly. Let me do this. Okay. Okay, so it would actually do, ooh, so difficult sketching. But now, what happens to the activation energy? It has actually increased. Okay, so activation energy, well, basically the particles, what you would say is the number of particles that have energy, or number of particles they have energy that is higher than the activation energy. Okay, so most particles can now react, so therefore they can react. The reaction can, happen. And what can you conclude, therefore? Well, we can conclude that you'll have more effective collisions. Okay, and therefore your rate of reaction will also increase. So that is what happens when you increase concentration. Okay, the number of particles under the graph, they increase. Your most probable energy stays the same. The number of particles that have the most probable energy have increased. The number of particles that have gained, or rather have energy that is higher than the activation energy, they're actually more. They've also increased, therefore you'll have an effective collision. Okay. When you decrease concentration, however, okay, the opposite will happen to what happened when you increased concentration. So again, you start at the same place at 0, but now okay, I tried. Yeah. So basically, again, the most probable energy, it will stay the same. Okay, but the number of particles at the most probable energy, they definitely have decreased. Okay, the number of particles overall have decreased. Okay, and also, what did I want to say? The area under the graph has also decreased. Okay, so number of particles, they have decreased. Okay, the most probable energy, it also remains the same. And then the activation energy, as you can see here, okay, the number of particles that have energy that exceeds the activation energy, that actually decreased. So activation energy, those number of particles, okay, I should have written here, number of particles that have energy bigger than that have increased when you increase concentration, but when you have decreased concentration, so the number of particles that have energy higher than the activation energy have actually decreased. Okay, therefore not a lot of them react, so not a lot of reaction happening there. Okay, and therefore what can we conclude? The effective collisions have actually decreased. Okay, therefore the rate of reaction as well would have decreased. Okay, so yeah, this is basically how it looks when you have decreased concentration. Okay, you actually have taken away some of the particles. Now we get to adding of a catalyst. What does a catalyst do? Okay, I have a graph only for adding a catalyst. I'm not, because in metric you're only dealing with a positive catalyst, not a negative one. So we're not going to look at the effect of adding a retardant. A retardant is the opposite of what a catalyst does. A catalyst is speeds up the rate of reaction, whereas a retardant, it actually slows down. So we're not looking at that. We're going to just look at the addition of a positive catalyst. So what happens there? Let me just use a different color. So here, the most probable energy stays the same. Okay, so, number of particles, well, they do not change, so they remain the same. And then the most probable energy, it also remains the same. And now the activation energy, so what the catalyst does, and you would know that by if you look at your exothermic graph or endothermic graph, the energy versus time graph, you will see that the catalyst actually lowers the activation energy. Remember, so yes, it will lower it. So if the activation energy before was 300 joule, what the catalyst does, it lowers it maybe to like 200 joules. Okay. Okay, so yes, the activation energy has been lowered. So activation energy is lowered. Therefore, you will have more particles that have energy that is greater than the active energy, okay? And therefore can react. Alrighty, and what can we conclude? Well, with the addition of a catalyst, you'll have more effective collisions. Okay, and therefore your rate of reaction actually increases. Rate of reaction increases. So yeah, that's pretty much it. I'm gonna load an exam question so that we see how we can apply all of this knowledge. Okay, so I found a paper, paper 2, 2016. It's a November paper, and yeah, I found the Maxwell-Boltzmann distribution diagram. So let's see what kind of questions they would ask. If you can see here, it's actually 2 marks out of 150, but it's a nice 2 marks to bag. Okay, so it says 3 energy distribution curves for the oxygen gas produced under different conditions are shown in the graph below. The curve with the solid line represents 1 mole of oxygen at 90 degrees Celsius. Okay, before we even look at the questions, look at P. Okay, if you were to look at P, you would see that the most probable energy is actually the same to the original graph. Okay, if the most probable energies are the same, it means either the concentration was increased or decreased, or it means there's a catalyst. Okay, because we had 3 conditions. We looked at temperature, we looked at concentration, we looked at a catalyst. And the cases where the most probable energy was the same is when you added a catalyst or you increased or decreased concentration. Okay, the most probable energy for the other graph has shifted to the right. And as you can see, the maximum with graph Q is actually less, but with the shift of the most probable energy to the right, we know that we have an increase in temperature. Okay, so if the solid line was 90 degrees, then Q is definitely more than 90 degrees. Okay, and then it means that, so yeah, the only place where your activation energy would actually shift is when you have added a catalyst. So in this case, I don't think any catalyst was added, but so it means that the activation energy is the same for all of them. Okay, let me just change color and remove this. I don't know how to remove it, but yeah, so basically the activation energy is the same for all of them. Okay, so now let us see. So we need to choose the curve P or Q that best represents each of the following situations. So initially we had 1 mole of oxygen at 90 degrees. Now it says 1 mole of oxygen gas produced at 120 degrees. So remember, if you increase temperature, you do not change the number of particles under the graph. Okay, the number of moles stay the same. So I would say then for 5.3.1, that would actually be Q. Now, 2 moles of oxygen gas produced at 90 degrees. So now we have kept temperature constant, but there are more moles. So we have actually increased the concentration. Okay, if you have increased the concentration, like I said, the most probable energy remains the same. So that would be Q. P. Why am I saying Q? That would be P. Okay, guys, so basically that's how you do these questions. This was a fair simple one. If you want to see more examples, please do see the past papers that we have done on our YouTube channel. Okay, and please do not forget to like our videos as well as subscribe to our channel. Alright, and if you want a private lesson, do book it on our website www.mvtutors.co.za, and thank you for tuning in.